And also Alex, once again, we're going back to the notes from 2 lessons ago. There's one last theorem that we have to do. It was in the lesson called finding limits by using analytical methods. Okay, so the squeeze theorem, when you hear it, is going to sound pretty obvious, but there's an actual theorem for it. So the squeeze theorem is a technique used to confirm the limit of a function by comparison with 2 other functions whose limits are known or easily computed. Okay? Consider some function f of x is trapped between 2 functions. Okay, so here's the idea, because there's a lot of words there, and here's basically the idea of it. Let's say we have some kind of like weird function. Okay, and let's call this, okay, so we have some weird function there. Okay, and let's call this g of x. And let's say we want to find the limit right here, but we don't know how to deal with the g function. Okay, so one thing that we can do is we can trap this function by 2 other functions we are familiar with. So for example, let's say I make a parabola here, and I make another parabola right there. I could deal with those functions because I know how to deal with parabolas. Okay, let's call this f of x, and let's call this h of x. Okay. Now, I know that f of x, just by looking at the picture, f of x will always be less than or equal to g of x, which will always be less than or equal to h of x. Yael, this is from the notes from 2 lessons ago. So I know this is the case, right? Okay. Now, if you're able to find, because I know how to deal with the f function and the h function, so let's say the limit as x approaches c of the f function is equal to L, and the limit of the h function is equal to L, because these are the functions you know how to do. You know how to do f and you know how to do h. And let's say at this point you find that the limit is L, then by the squeeze theorem, the limit as x approaches c of g of x is also equal to L. Okay. It kind of seems really like, oh, that it's kind of obvious by looking at the picture, because they're all equal to each other right there. But this is the theorem that goes behind the concept. I don't know what to do with this unknown function, so I'm going to squeeze it between 2 functions that I know how to deal with. And then if I find the limit of this lower function and the limit of the upper function, and they're equal to each other, then the limit of this unknown middle function should also be the same. Okay. So let's go to the back, and we are going to do this first problem here. So example, if 1 is less than or equal to f of x is less than or equal to x squared plus 2x plus 2, find the limit as x approaches -1. Okay, so let's do that. So I know by looking at this, f will always be in between 1 and f will always be between x squared plus 2x plus 2. This is a parabola. And I don't know what f of x looks like. But this kind of looks like I could use the squeeze theorem. So what I'm going to do is I'm going to find the limit of this left function, and I'm going to find this limit of the right function. So let's go ahead and find the limit as x approaches -1 of 1. Okay. And we all know that this is just going to be 1, right? The limit of any constant is just the constant itself. Okay. Now, give me a second, make sure. Now let's find the limit of the right function. Okay. Now we know how to do that. That's just plugging the -1 in because it's a continuous function. So this is -1 squared plus 2 times -1 plus 2. This is equal to 1 minus 2 plus 2. Okay. And 1 minus 2 is -1. -1 plus 2 is equal to 1. So since the limit as x approaches, since the limit as x approaches -1 of 1 is equal to the limit as x approaches -1 of x squared plus 2x plus 2, okay, then by squeeze theorem, the limit as x approaches -1 of f of x is also equal to 1. Okay. We're going to do more squeeze theorem with today's notes. So we'll just skip example 5 for now, because we're going to do more squeeze theorem anyway today. So for today's notes, go ahead and start with the top. Take a couple of minutes to do those 3 problems on the top, and then we'll continue with the lesson. I'll have the quizzes graded today. I was supposed to do it last night, but then I looked at the notes and realized I wanted to change things with the notes. So that's what I was working on last night. For number 2, no matter which method you do, remember to put a 0 term because you're missing the x term here. Okay, number one's a logarithm. So remember, this is just asking 3 to what power is 1 over 27. Well, I know 3 to the third is 27, but since the 27 is in the denominator, then it has to be negative. So this is equal to -3. Right? Remember, negative exponents mean you are going to flip the fraction. Okay, there are multiple ways to do number two. I don't even want to do the long division way, but for those of you that did the long division way, this is how you set it up. Okay. And x goes into 3x cubed, 3x squared times. Okay. If you subtract this, this becomes positive 12x squared. Then this becomes 10x squared. And then drop the 0x. X goes into 10x squared 10x times. 10x squared minus 40x. Hope I'm doing all of this right. This is minus, this is plus. I'm going to do it by synthetic just to double check. And this will be 40. So 40x minus 160. And you should have a remainder of 10. Okay, I don't know how many of you actually tried doing that, but if you remember the synthetic division way, it's much faster. So you ask yourself, what makes this 0? That would be 4. You put that in your little box here. And then you take the coefficients, which is 3, -2, 0, and -150. And if you remember this process, all you do is you bring down the 3 here. 3 times 4 is 12. -2 plus 12 is 10. 10 times 4 is 40. This is 40. And then 40 times 4 is 160, which is 10. So if you started with an x to the cube power, you would just drop the power. So this is 3x squared plus 10x plus 40, and then plus the remainder. So this is plus 10 over x minus 4, which is the same thing we got there. So yeah, if you know how to do synthetic division, that is much faster. Number 3, this is the inverse trig. This one should be, remember what this is asking you is what angle has a sine of 1/2, right? And remember that if you're dealing with inverse sine, you're only dealing with quadrants 4 and quadrants 1. So we're in quadrant 1 since it's positive. So what angle has a sine of 1/2? That would be pi over 6. You are going to know how to do inverse trig, okay? Which is just knowing your unit circle. Not for today's class, but later on in the semester. Okay, so now let's actually go and find limits of trig functions. So most of the work we have done with limits have been with polynomial and rational functions. So now we're going to go and talk about the techniques with trig functions. Several methods to use. Example 1 is like the method that we've always tried to do, which is just substitute. Okay. So if we substitute, we can remove the limit already. And so this becomes cosine of 2 times pi over 3 all over pi over 3. Okay, cool. This is fine. We don't have 0 over 0. So this works. So this is going to become cosine of 2 pi over 3 all over pi over 3. And knowing our unit circle, 2 pi over 3 is 120 degrees, right? And so what is the cosine of 120 degrees? Well, 120 is just the 60-degree angle in quadrant 2. So for 60 degrees, you should know that the cosine is 1/2. So this is negative 1/2 all over pi over 3. So you're going to need to know your unit circle for this lesson. Now, don't forget how to divide fractions. Remember, when you divide fractions, it's really the same thing as multiplying by the reciprocal, right? Negative 1/2 divided by pi over 3 is negative 1/2 times 3 over pi. And so my final answer here is negative 3 over 2 pi. That's my limit for that function. So letter B, 3 times sine squared theta. Cool, I don't have a fraction here, so I'm pretty sure I could just plug that in and not worry about any indeterminate form. So if I plug that in, remember sine squared theta is really sine theta squared, right? So this is 3 times sine of pi over 2 squared. And sine of pi over 2 is 1. And then so 1 squared is 1, 3 times 1 is 3. Okay, so let's try example 2. Let's go ahead and plug in pi over 2 here. So I have sine of pi over 2 minus 1 all over cosine of pi over 2 squared. Okay. So sine of pi over 2 is 1. And the cosine of pi over 2 is 0. So now what happens here is we have the indeterminate form. Okay. Whenever we get 0 over 0, please do never put undefined or anything like that. We have to do other techniques in order to find this limit. Okay? So let's think about this. We're going to use trig properties, actually. So one of the most important trig properties from before is this one. Sine squared theta plus cosine squared theta is equal to 1. Okay, and so I have cosine squared theta. If I solve this for cosine squared theta, everything's going to be in terms of sine, right? So if I subtract sine squared theta from both sides, I get that cosine squared theta is equal to 1 minus sine squared theta, right? You should be able to all manipulate this to get whichever one you want. Cosine squared is always 1 minus sine squared, and sine squared is always 1 minus cosine squared. Okay, so let's see what we can do with that. Let's change this. So this will be the limit as theta approaches pi over 2. The top is going to stay the same. But the bottom, we're going to use this property here. And we have 1 minus sine squared theta. Now, a lot of you are thinking, oh, can we just cancel that? Well, we can't because this is sine squared and this is sine. But if you remember, we could kind of factor the bottom because 1 minus sine squared is actually a difference of squares. This is the same thing as x squared minus 9. Okay. And I could break it up into x plus 3, x minus 3, right? You take the square root of both sides. This can also break up. 1 is a perfect square. Sine squared is a perfect square. If you remember from pre-calc chapter 7 when you were doing all those trig identities, one of the techniques that you were given was that you could factor trig things, trig expressions, not things. So let's go ahead and factor that. So the top is still sine theta minus 1. And then the bottom is 1 plus sine theta, 1 minus sine theta. Okay. Now we can cancel the sine theta minus 1 and the 1 minus sine theta. But remember, they're subtracting and they are switching places. So if you cancel these, you have to make sure you put a -1 right here because one is sine theta minus 1 and the other is 1 minus sine theta. So this will become the limit as theta approaches pi over 2 of -1 over 1 plus sine theta and then now you can substitute it in. So this is equal to -1 over 1 plus sine of pi over 2 the sine of pi over 2 is 1. So this is just -1 over 1 plus 1. And so the limit of this function is -1/2. Okay, so we did a lot there. We found that it was indeterminate form. We saw that we needed to use trig properties to manipulate our trig expression. We factored by using difference of squares, canceled, remember that this is -1, and then after that, you can just substitute. Okay, but that's a whole process you have to go through. Right here, because think about like on any normal, so Nathan, you're talking about here, right? So going back, like when you have a rational expression and you have x plus 3, x minus 3, all over 3 minus x, you can cancel x minus 3 and 3 minus x. They're not the same thing, but they're subtracting and they're opposites. So you can cancel this, but you just have to put a -1 here. So if you see here, the top is sine theta minus 1, and the bottom is 1 minus sine theta. They're kind of like the same thing, except the first and the last thing are switched, right? So same thing happens here, x minus 3 and 3 minus x. You can still cancel those, but you just have to put the -1 out in the front, okay? Anytime it's addition, you could just cancel without putting any -1, right? Because addition is commutative. So addition, the order doesn't matter. But when you're subtracting things like that, you have to leave the -1. Okay. So we're gonna have more practice with this. Don't worry. Let's go to the back. So here are important properties to remember. Okay. Here is the Pythagorean property. And you also learn what were called double angle formulas from trig. Sine 2 theta, cosine 2 theta. And we'll get to these in a bit. But I want you to see if you can try to do A by following the method that we did on example 2. Just play around with it, okay? See how far you can get. Okay, so let's see how far you got here. So if you try plugging in 0, you would get 1 minus cosine 0 over 2 times sine of 0. Oh, sorry, I'm putting theta, but they should be zeros, squared. And I know cosine of 0 is 1. And I know sine of 0 is 0. So this will be 0 over 0. Okay. You don't necessarily have to show me the step that gets you 0 over 0. If you can just see that in your head and be like, oh, cosine of 0 is 1 and sine of 0 is 0. So I know it's going to be 1 minus 1 and 0 on the bottom. You don't need to show me that you're plugging in and getting the 0 over 0. Okay. But once you determine it is 0 over 0, now what do I do? Well, I have sine squared on the bottom, so what I'm going to do is I'm going to use the Pythagorean theorem to solve for sine. So if I solve for sine, then sine squared is equal to 1 minus cosine squared theta. So this is the limit as theta approaches 0. Okay, so there's a 2 out there, so I'm going to leave the 2 out there. I'm not doing anything with the 2. And then this is going to be 1 minus cosine squared theta. So once again, I did what I did on the front page, right? The Pythagorean identity, I made sine squared equal to 1 minus cosine squared. Now, once again, I see that I could probably cross that out if I factor this. So I'm going to use difference of squares. So the limit as theta approaches 0 of 1 minus cosine theta. And then the bottom is going to be 2, 1 plus cosine theta, 1 minus cosine theta. Okay, so here I could cancel the 1 minus cosine theta and the 1 minus cosine theta. They're the same thing. I don't need to put some kind of -1 or anything. So I could cancel these, and I'll have the limit as theta approaches 0 of 1 over 2 times 1 plus cosine theta. Now I can just substitute the 0 in. So this is 1 over 2, 1 plus cosine 0. And that's equal to 1 over 2, 1 plus 1. Cosine of 0 is 1. And then this is going to be equal to 1 plus 1 is 2. So it's, I skipped the step there, but you should know that that's 1/4, right? 1 plus 1 is 2. 2 times 2 is 4. Limit is 1. Okay. Letter B is actually pretty easy. So if you could see this in your head, 2 times pi over 2 is pi. Sine of pi is 0, and cosine of pi. Okay, let me just do that. I'm just going to show its indeterminate form. But once again, you don't necessarily have to show this. So if I do this, this is sine of pi over cosine of pi over 2, which is 0 over 0. Okay. So it's indeterminate form. But this is one of the simplest indeterminate forms that you can do because I have sine 2 theta, and that's something we have here, right? That I can change it to that. So let's go ahead and do that right now. This is the limit as theta approaches pi over 2. Sine 2 theta is 2 sine theta cosine theta. So I'm using that identity up here, all over cosine theta. Cool. Cosines cancel. So this is just the limit as theta approaches pi over 2 of 2 sine pi over 2. So now we can just plug that in. 2 sine pi over 2. And the sine of pi over 2 is 1. So my limit is 2. Now, C and D deal with cosine of 2 theta. Now, if you look back at the top, and we're going to go back to these properties here, there are 3 separate identities for cosine of 2 theta. Yeah, Caesar, 0 over 0 is not really wrong. It's called indeterminate form. And when you get 0 over 0, you have to do other techniques to find the limit. Because 0 over 0 does not mean there is no limit. It means that there might be a limit, but you can't do it by direct substitution. Okay. So let's go ahead and look at these 3 properties here. Now, you're going to look here and you're going to ask, which one should I use when I see cosine 2 theta? Well, it's going to be kind of obvious because these are all perfect squares. So remember how, or they could be broken down by difference of squares is what I'm saying. So remember from the front page how we broke up, how I said x squared minus 9 is really x plus 3x minus 3. How 1 minus sine squared is 1 plus sine, 1 minus sine. What we're going to do is we're going to look at these and see if we can break them up any further. So cosine squared minus sine squared, this can be broken up into cosine theta plus sine theta, cosine theta minus sine theta, right? Because these are 2 perfect squares, so I could break these apart. Now, the 1 minus 2 sine squared theta doesn't look like a perfect square because the 2, you're like, 2 is not a perfect square. You can't break it down. But if you could break anything down. So for example, let me show you an example here. X squared minus 7, even though you can't really factor that because there is no way to break down 7, technically you could do something like this. X plus root 7, x minus root 7, right? This creates that because root 7 times root 7 is 7. So here, I could break this down into 1 plus root 2 sine theta and 1 minus root 2 sine theta. The 1's break down into 1 and 1. The sine squared is sine and sine. And then the 2 is root 2 and root 2. Same thing happens down here. I could break this into root 2 cosine theta plus 1, root 2 cosine theta minus 1. So I just use difference of squares to do all of that factoring. Okay. So let's do letter C. Now, this is indeterminate form, and I'll show you one last time. If I plug in negative pi over 4, and I'm going to need some space here, I get 1 plus root 2 sine of negative pi over 4 all over cosine of 2 times negative pi over 4. Okay. Now this is 1 plus root 2, the sine of negative pi over 4. So now we're in quadrant 4. Sine of pi over 4 is root 2 over 2. So, and we're in quadrant 4, so it's negative root 2 over 2. All over cosine. And if we do this, this is negative pi over 2. And then now remember, root 2 times root 2 is positive 2. So this becomes 1 plus, no, sorry, I forgot the negative sign. 1 minus 2 over 2 all over 0. And 2 over 2 is just 1. So this is 0 over 0. Okay. But I think what you can do is you can just assume that if you see a double angle formula, you're probably going to use double angle formula to simplify it anyway. So the indeterminate form, once again, you don't necessarily have to do this step if you can recognize that you are going to be using trig properties. So that's the last time I'm really going to do indeterminate form. It takes too much time to go through it. Now, so I see I have cosine 2 theta here. So if I go here, the idea is I probably want to cancel with something on the top. So if I go to these things, it's like, which one of these can I use to cancel with that? Well, it's kind of obvious. I want to use this because it will cancel with that. Okay? So this is going to be the limit as theta approaches negative pi over 4 of 1 plus root 2 sine theta. Okay. All over one minus 2 sine squared theta. I'll be okay if you skip this step and you go straight to the limit as theta approaches negative pi over 4, but I want to show you all the steps here. 1 plus root 2 sine theta. And then what I'm going to do is I'm going to use that this breaks down into all of that. So this is going to be 1 plus root 2 sine theta, 1 minus root 2 sine theta. That cancels. So this is the limit as theta approaches negative pi over 4 of 1 over 1 minus root 2 sine theta. And now you just plug negative pi over 4 in. So this is 1 over 1 minus root 2 sine of negative pi over 4, which is 1 over 1 minus root 2 times root 2 over 2. Now, negative. Sorry for running out of space here. So you have to be careful with a lot of things here. Your signs, that you're doing your multiplication correct. So negative times negative is going to become positive. Now, what is root 2 times root 2 over 2? Well, remember, root 2 times root 2 is just 2. So this is going to be 1 over 1 plus 2 over 2. 2 over 2 is just 1. So this is going to be 1/2. Okay. So you try D on your own. It's almost the same exact problem as letter C, except you're using a different trig property. It's okay if I just want you to try it out. Okay. You don't need to show its indeterminate form. For time purposes, I'm going to tell you its indeterminate form. So go ahead and just use the properties up above. Okay, so you're confronted with a cosine 2 theta, so you have to think, which one of the above ones do I have to use? Well, I see that the bottom is root 2 cosine theta minus 1, so I'm going to use the bottom one, that this should be the 2 cosine square theta minus 1 all over. Okay. However, on the homework, if you want to skip this step and just go straight to the difference of squares factoring, I don't mind. These questions will never be, I don't think they'll ever be free response questions anyway on the AP test. They are probably going to be multiple choice questions if you ever see them. So I know the top is going to factor by using difference of squares. Oh, this is pi over 4. So this is going to be root 2 cosine theta plus 1, root 2 cosine theta minus 1, all over root 2 cosine theta minus 1. So pretty straightforward here, these cancel. And so I just have the limit as theta approaches pi over 4 of this. So if I plug that in, I get root 2 cosine pi over 4 plus 1. Cosine of pi over 4 is root 2 over 2. So this is root 2 times root 2 over 2 plus 1. Root 2 times root 2 is 2. So this is just 2 over 2 plus 1. And so I should get 2 there. Okay. Okay, E and F are more, if we have time, we'll get back to these, but if you could do those top 4, then you should be actually good for the homework. This is just extra manipulation for E and F. If we have time, we'll get back to them, but I do want to go to the next type of limits. So any questions on these 4 problems? Okay, this is using the Pythagorean identity, and then these are using the double angle identities to get you limits after doing indeterminate form. Okay, so special trig limits. There are 2 trig limits that are known. So the limit as theta approaches 0 of sine theta over theta is equal to 1. And the limit as theta approaches 0 of 1 minus cosine theta over theta is equal to 0. Okay, so what we're going to do is we are going to look at a couple of limits and see if we can use these properties to help us. So if I look at the first problem, I have limit as theta approaches 0 of sine of 2 theta over theta. If I try plugging in 0, you see that I'll get sine 0 over 0, which is just 0 over 0. That's indeterminate. Okay. So what am I going to do here? Okay, well, I know that if this angle and this angle are the same, sine theta over theta is equal to 1. I don't have that here. I have sine 2 theta, and the bottom is theta. So why don't we just make the bottom 2 theta? So what I'm going to do is I'm going to multiply the top and the bottom by 2 over 2. You cannot just multiply the bottom by 2. You cannot do that. Remember, if you're multiplying a fraction, to keep a fraction equivalent, you have to multiply the top and the bottom by the same thing. So what happens here? Well, this becomes the limit as theta approaches 0 of 2 sine 2 theta all over 2 theta. Well, look what happens now. I have sine 2 theta over 2 theta. These angles match. So I know that this is equal to 1. So this is just 2 times 1 is equal to 2. Okay, let's look at letter B. It's kind of like letter A, but now I have sine of 3 theta over 4 theta. And remember, you want these to match so that we can use this special trig limit here. And so you're thinking, well, 4 is already past 3. What am I going to multiply this to make sure that I could get this and this to match? Well, that's actually kind of easy if you kind of know the little trick. Just take, if you want to get any type of number, hold on. So for example here, if I have the number 2, what can I multiply it to get 5? Well, that's simple. It's just 5 over 2 because the 2's are going to cancel and I'll end up with 5, right? If I have 3, what can I multiply it to get 7? Well, that's easy. I want the 3's to cancel, put the 7 on the top, right? So same thing here. What if I want to get this bottom 4 theta to be 3 theta? Well, I'm just going to multiply the top and bottom by 3/4. So same idea here, right? The 4's are going to cancel and it's going to leave a 3 here. So this is going to turn into the limit as theta approaches 0 of 3/4 sine of 3 theta. And then what's 4 theta times 3/4? Well, that's just 3 theta. That's the little trick that I use here, right? And if you need to see it like happening mathematically, 4 theta over 1 times 3/4 is 3 theta, right? But now sine 3 theta over 3 theta, I could use this limit. That's equal to 1. And so I don't actually have to plug anything in because all I'm left with, well, it's really 3/4 times 1, but that's just 3/4. Okay. See if you can do letter C. It's kind of like letter B. You want to get the bottom to be 5 theta. Okay, so think, what are you going to multiply by? Hopefully you realize that you're going to multiply top and bottom by 5 halves. Okay. So if I do that, I get the limit as theta approaches 0. 3 times 5 halves is 15 over 2. Please, I don't really see it that much, but 3 times 5 halves is 15 over 2. It's not 15 over 6. Do not multiply the top and bottom by 3. Remember, it's 3 over 1 times 5 over 2, 15 over 2. Sine of 5 theta all over 5 theta, right? And if you really need to see that worked out, 2 theta over 1, the 2's cancel and you're left with 5 theta. Okay? But I know this is just 1, so my answer here is just 15 over 2. Okay, let's look at letter D. Once again, you can see it's indeterminate form. Cosine of 0 is 1. So 1 minus 1 is 0, and then sine is 0, so you get 0 over 0 here. So look what I have here. I have 1 minus cosine theta. So if you go up here, you can see that I have, it looks like this, but there's this other sine 3 theta that's here. So what I'm going to do is, remember that you could do this in math. If you have x plus y over 2, this is the same thing as x over 2 plus y over 2, right? So I'm going to go ahead and do that here. I'm going to break this up using limit properties. So this is the same thing as limit of theta approaches 0. And so I could break this up into 1 minus cosine theta over theta plus the limit as theta approaches 0 of sine of 3 theta over theta. Now I can use my special properties up there, my special limits, because I know the limit as we approach 0 of 1 minus cosine theta over theta. This is going to be 0. All of this is going to be 0. And this, we actually know what to do because we were doing it for parts A, B, and C. Right? This is where we're going to multiply the top and bottom by 3 over 3. So I know this is going to be equal to 0 because this whole thing goes to 0, plus the limit as theta approaches 0 of 3 sine 3 theta all over 3 theta. And then I know that sine 3 theta over 3 theta becomes 1. So all I'm left with here is the limit as we approach 3, which the limit of any constant is just the constant itself. And that's 3. Okay, try letter E. Same, almost kind of the same thing as letter D. Sorry. It's almost the same thing as letter D where you have to split it up. So we split it up. I get the limit. So my first thing is 3x over x. And then this is sine of 6x over x. Well, I know that this looks like the limit that I have on the top. I just need to multiply top and bottom by 6. 3x over x is just 3. And then this is 6 sine 6x all over 6x. And then using the property from above, sine of 6x over 6x is just 1. So this is the limit of 3 plus the limit of 6, which is just 3 plus 6, and that's 9. Okay. Okay. For now, let's skip F. I think with all of that, you have enough practice. And let's skip the DIY. I want to get to example 5 on the back because we're going to use Squeeze Theorem as the last thing we're going to do today. If you want, you could do those practice on your own, but I would just do the homework. So let's say we wanted to evaluate this limit. You're like, oh, well, can't we just substitute? And you're like, no, we can't really because sine of 1 over 0 doesn't make sense. Okay. So let's see if there is a limit. So once again, we have some mystery function here, and we want to know the limit as x approaches 0. Now, you have to remember one thing. What is the range of sine? Well, let's remember that sine, the highest sine value you can have is 1. The lowest sine value you can have is -1. Remember, the unit circle goes from at the bottom, sine is -1. At the top, it's 1. So I know this is true, right? So here I have sine. So it doesn't matter what x is, right? Sine of anything has to be between -1 and 1. So here I have sine over 1 over x. So I know that sine of 1 over x has to be between -1 and 1. Because if you take the sine of anything, it has to be between -1 and 1. So this already kind of looks like I'm going to apply the squeeze theorem, right? Because I have two things on the left of this thing, to the left and right. So we could squeeze it. However, does this function match this function? No, it's missing the x squared. So if I put an x squared here, I'm multiplying this by x squared. But remember, if we have an inequality, if you do it to one side, you have to do it to the other side. But there are couple of things here. If you remember from Algebra 1, you had stuff like this, right? And if you did this, you had to do that, and you had to do that, right? So same thing here. If I'm going to multiply this middle one to look like this, I'm going to put an x squared right here. I'm multiplying by x squared. But if you do that, you have to multiply everything by x squared. So multiply by x squared. So this is going to become negative x squared less than or equal to x squared sine of 1 over x less than or equal to x squared. Well, I want to find the limit as x approaches 0. I know how to deal with that function. This is just a parabola. I know how to deal with that function. That's also a parabola, right? So the limit as x approaches 0 of negative x squared equals 0. And the limit as x approaches 0 of x squared is also equal to 0. So since the limit as x approaches 0 of negative x squared is equal to the limit as x approaches 0 of x squared, then by Squeeze theorem, the limit of the middle function has to also equal 0. So that's how we can apply the Squeeze theorem. Okay. Same thing here for this DIY. You should also know that right? And you could do the same steps that we did on the top. Okay. So that's it for today. I'm gonna assign homework that's gonna be due Monday night. So you have a weekend. So you have 3 days to do it. Try to get it done this weekend so you can turn it in. I could tell you what your mistakes are. And so you don't have to worry about it Monday. Someone has a question. Yes, and I'm gonna post this recording to Google Classroom. So you can go over how to do these problems again if you need help. Okay, so I'll post that homework either right now or after the next period, so you'll have it ready to go. Okay, so I'll see you all Tuesday. Have a good weekend, everyone.